Hi, we are Anna and Dominic, and we're here to tell you something about brain-computer interfaces. I'm a mathematician, and he's a cognitive scientist, so we are in this topic. First, we'll tell you why we are excited about this topic. Then we'll dive into the technical details, how data is represented inside of the brain, how to read it out with the computer, and how to build your own BCI. And finally, we'll have a quick discussion and answer some questions. So let's talk about communication. Language is the most natural way to communicate with your fellow human. It's the most intuitive way of expressing your thoughts and also the most common method to communicate with your computer. Obviously, the word is very powerful. But which devices can we use to put the words from our minds into a computer? Of course, there's the keyboard. Compared to talking, it's quite slow and quite hard to learn, but extremely accurate by design. There are all kinds of motion tracking tools. The mouse, the touchpad, touchscreen, graphic tablet. Because we want text input, we need to use handwriting. Higher information density, easier to use than a keyboard, but very slow at actually transferring a message. Then we have voice input. Everybody knows that dictating is much faster than writing. But since a couple of years, even our computers understand what we say. This could become very interesting in the long run, because talking raises the transfer speed limit considerably. Have you thought about the information transfer that's really happening here? Because the actual chain of information looks more like this. It's the brain that sends the information to a body part, which interacts with the device that sends information to the computer. And both ends of the communication can deal with much higher data rates than measly 15 bytes per second. That's so the measurement. So what would happen if we cut out the middleman and connect the device directly to the brain? So as for language, spoilers, it would be surprisingly underwhelming. Thinking words isn't that much faster than speaking them. When you read out the words from your brain, the data quality is horrible, there would be a lot of misunderstanding, and you would have to teach the software where the words are in your brain. So you'd need a couple of hours before you could get even started. But of course, with such an interface, you could also use something else than words as input.
For example, let's look at art. When I imagine a picture and we want to show it to other people, I can just pick up my canvas and take a paintbrush and start painting. Or I could also use a graphics tablet to paint with a virtual brush. Or I could use a specialized mouse to put together 3D objects and render the scene. But each of these strategies is going to cost me several hours. And even if I actually had some knowledge in painting, the end result would never look exactly like my imagination. Here's why a brain-computer interface is starting to shine, because it can access the image in your head entirely and immediately. There's not just arts and language, there's also gaming, there's music, there's interfaces everywhere. Interfaces that are hard to learn and even harder to master. Interfaces that put a limit on our creativity. Having a really good brain-computer interface would make lots of these devices redundant. And as soon as a computer can guess what you want to do, a lot of frustration starts to disappear from learning. And since there's more to the brain than just hearing and seeing, maybe it makes sense to transfer data from other senses as well. Unfortunately, this is still very much a vision into the future. But we have already today some serious possibilities of controlling a computer with our minds. It's not even that expensive, but I'll come back to that in the last part of our talk. Before we can build a system that can read from our brain, We need to know how the data is represented in there. For that, we need to take a look at the very basic map of the brain. We see and imagine with the back of the brain. It's called the occipital cortex. Hearing and talking happens in the lower side areas. It's directly next to the ears, which makes sense. The top of the brain is responsible for skin and muscles and movement in general. And what the front part does is most difficult to understand, and even for scientists. So let's just say it does the actual thinking. So let's start with a simple example. Let's imagine a red ball. First, we look up the meaning of a red ball in the meaning library down here. Then we send this object to the appearance library in the front. This area is a library of visual objects. It resolves the object code into its color and shape codes, which are immediately sent downwards. Color and Shape Center then convert these property codes into their visual meaning and build up a link to the correct space in the visual buffer. As soon as this connection is established, we see the image of a red ball in our minds. This red ball is, of course, stored somewhere in the brain too, along with millions of other data sets. All this information is stored in the connections between neurons. Neurons never work alone because they're too weak. I'll explain that in a minute. To create a meaningful signal, they have to work together. And they do that in groups of hundreds of neurons, which is called a mini-column. Each mini-column stores one unit of information. Together with 100 other mini-columns, they form one memory unit called a hypercolumn. They're organized in like this, column forms. Each one of these hexagonal memory units is incredibly flexible. They can remember everything about red balls, how it looks, how it feels, how it sounds like, and even your emotions toward red balls. But because we only have 2 million hypercolumns, it would be a waste to use a separate one for every ball. And that's why your memory unit for red balls is the same unit as for green, black, blue, and green and yellow balls as well. So, what happens when a hypercolumn of neurons recognizes the special ball from your childhood? It activates the mini-column. It stores the emotion of your childhood. Before, all the neurons in this mini-column were just idling. Their activity was low, random, slow, and completely desynchronized. But as soon as the activation signal arrives, they generate waves of activity. Now each one of these yellow dots in the bottom is the activity of a single neuron. Because single neurons can only generate a short flash of activity, they have to work together and produce these waves. These waves are the typical data format inside the brain. Waves can encode more information by changing frequency and phase. The amplitude, however, is mostly the same. And in this case, this wave is part of the memory of the red ball of your childhood. In case you were wondering, this is how hypercolumns communicate with each other in slow motion. This is a slow motion part of the actual cortical surface simulated from a rat cortex. You see that there's some structure and some clear loops, but it's all flowing, shifting, and never really repeating. There's some nodes, there's some loops, and all of these loops are forming in the later stages of the brain more complex and and larger loops. And these are what we perceive as information. This is how all these electrical waves are traveling through the brain. Mm-hmm.
Okay. So before further, I give a short math warning. I will use some formulas. Please don't be,
Don't be alarmed.
Yeah. It's okay. They won't do anything. What we now have to do is to find the origin of these electrical waves. So how do we do this without physical access to the brain? Well, the easiest and already established way is to use an EEG. This is a device that measures electric fields with the help of some electrodes. There are EEG used for research or medical purposes. That's some of this. And also smaller ones for consumers, like this one on the other side. They differ mostly in the price and the number of used sensors. You have probably seen one in the media already. Dominic will later explain how EEGs work. For now, it's sufficient to know that EEG measure electric fields. The big question is now, how does this all work? The electric field from each neuronal cluster is strong enough to be measured outside of the head. It is usually between 200 and 500 millivolt. The electrodes of an EEG are placed all over the head. We have to place the electrodes directly onto the head surface because air conductivity is very low. Then we combine all the electrodes, electrode voltage, so that we know the voltage for each point on the head surface. Neuron clusters also produce a magnetic field at the same time. This could also be measured from a small distance. But the device for measuring very weak magnetic fields are far too big to carry around and also very expensive. They also have to be isolated from other strong fields. Even regular watches create a magnetic fields that are magnitude stronger than the whole brain. The research for portable devices are already starting, but currently EEG are the only handy devices for custom usage. Since the electric field is caused somewhere inside of the brain, we have to look at what happens on the way outside. Our head consists of different tissues, which all put up some amount of resistance to electric fields. So instead of traveling straight through the head, the electric field gets distorted. It could a little be imagined like this. When jogging, you have different speeds on different kind of surfaces. When you are jogging on asphalt, you are quicker than on sand. It's the same with the electric field in our head. For example, our bones have a very high resistance, and the liquid around our brain is very conductive. And one brain tissue even has different conductivities for different directions. So it's get a little bit complicated here. We are finished with the electrophysical setup. Active neurons create an electric field inside of the head. We know about the conductivities of different tissue layers and the voltage on the head surface. Without any other knowledge, we are stuck here. Like in many occasions for solving problems, now we require the mighty toolbox of mathematical science to find a solution. What we want to do now, we want to translate our setting and our problem too into the language of mathematics, solve the problem there and translate the mathematical solution back into reality. And to warn you beforehand, within the mathematical world, there on the other side, we will need another translation into something a computer can solve. The first step, translating into mathematical language, is also called to model the problem. Building a mathematical model uses principles, laws, and concepts from other fields of science. In our case, we use a modified version of the famous Maxwell equation, which describe the connection between magnetic and electric fields and forces. They were first described by a physical scientist named J.C. Maxwell in 1865. Those equations can be simplified and adapted to our application. The equation we get as a result is written here. First, we look at the left side. The x describes any point in a head. U of x is the electric field at the position x. And when you derive that, you get the current at this point. Now you fold this with the electric conductivity and compute the divergence. That's what happens mathematically. What you can imagine happening in the left side is the difference between the incoming flow and the outgoing flow of the electric field at every point x. The right side is all about neuronal activity. What is written there is the so-called current dipole. This means that the whole equation is 0 everywhere except at the position of the activity. Together, this means for every point in the head, the same amount of electricity flows in and flows out, with the exception of the active neurons. So that was the equation. Let's talk about solving this equation. The usual way to solve this is to assume that the head connectivity and neuronal activity and the head connectivity and the location of the activity are already known. And you would start calculating the head currents. This is called the forward problem. But of course, we don't know the current location yet because that's something we want to compute. So we want to calculate the activity location from the conductivity and the measured surface voltage. For this, the equation needs to be turned around. This is called the inverse problem and is surprisingly difficult. We encounter the next problem when we look on these things we measure. We want to know where the activity inside the brain is located. So we measure the electric field on the head surface, but we cannot measure inside the head. That's something different over there. Medical EEG have probably around 120 sensors. So the measured electric field only has a resolution of 120 points. This gives us much less information than we actually need. We can deal with such kind of less information if we make some presumptions about the location of activity. Usually, we limit ourselves to places in the brain with actual neurons, namely the cortex. But of course, the resolution of our estimation gets better the more sensors we have. Once we have faced these problems, we now can convert the equation into a computer-friendly format. A computer cannot deal with equation that describes something for every point in the head. That would be infinitely many points, and infinite memory is still quite expensive. So, fortunately, some clever mathematicians developed algorithms for solving the problem, which are computer-friendly. We do not compute for every point in the head. Instead, we select only some points in the head, for example 1 million, and compute results only for them. We interpolate the areas between our selected points when we need a value there. Mathematically speaking, this selection process is called discretization. The continuous structures of the head are divided into small cells and of simple geometry. The continuous structures of the head, usually we use tetrahedra or hexahedra, or a mixture of both. This works well, and it can be mathematically proven that the error from the discretization is small enough for certain settings. For this approach to work well, we need a good 3D model of the head. And we haven't talked about the conductivity. That's the last part that's missing for our model. When building the 3D model, we need this model to represent the conductivity well enough. That's the next step then. The scientific way for getting conductivity values is to put the head of choice into an MRI. That is a big machine which can take high-resolution images of the inside of the head. Then we take such a good picture from this head and convert this picture into these little geometric cells. There is only one conductivity value for one cell. If you want to be very exact, you have to use a different head model for every person, because every head is unique. And because the brain can move around inside on the head, you should always measure your person in the same position. But when you don't need to be precise, there's a simple rule. Any head model is better than no head model. Then we are ready to estimate the location of neuronal activity. we take the conductivity model of our head, the location of the sensors, all the locations of all cortex points, and put all of this into this machine. This machine first puts all of this information together into one head model. It makes sure that all these little cubes and the sensor position and the cortex share the same coordinate system. The last data set makes sure that we only estimate locations of activity inside the cortex. When putting up these restrictions, you have to be sure of two things. First, the real location of activity is actually in the cortex, and second, that there is no activity outside of the cortex. With the head model, the machine then computes something in an intermediate step called transfer matrix or lead field matrix. The transfer matrix describes what the sensors would measure for every possible electric activity in the cortex. Building this matrix is a very time and memory consuming process. But the nice thing about this whole first part is that you can prepare it offline. So this means you only have to do it once. After the first huge calculation, only the last step requires some brain activity. This is over there. Since this last step can happen in a few milliseconds, this is perfect for real-time application. And if you always use your EEG in the same position on your head, and your cortex has enough points, there's no reason to change the transfer matrix. The next step takes this transfer matrix and the measured electric field. A good solver for the inverse problem then decides which was the most likely activity location that caused this sensor voltage. There are different ones, like MNE or S-Loretta, which give reasonable results. But still, these algorithms are a little too time and memory consuming to do this in a good online time. So in the end, you get an activity map that shows where the active clusters are. And to conclude my part, yes, we can estimate where our neurons are active. Our estimation would be much better if we had millions of sensors instead of 120. It would be much better if the sensors were inside of the brain instead of outside. And we still need a ton of computational power and memory. But it is possible, like Dominic will explain in a few seconds.
All right, we have finished with all the theory, and we're coming back to the real world now. Don't worry, it's not as hard as it sounds like. In the beginning, you can actually deal with not having the whole localization part and deal with sensor data only. But you will see that you run into a wall quite soon because your resolution isn't high enough. So the whole once you get there, you have to consider the part that Anne talked now about and actually create an activity map. So what do you need to build your own BCI? 2 pieces of hardware and 2 pieces of software. I'll start with the hardware. An EEG consists of 2 core parts, an amplifier and an analog-digital converter. You need both of these parts for every channel. Since these chips are relatively expensive, more channels automatically also means more expensive. We want a noise floor of at least 40 decibel for our amplifier to have a reasonable signal-to-noise ratio. The same is true for the ADC. The absolute minimum sampling frequency is around 100 Hertz, and you should go for 200 Hertz for a reasonable minimum. State-of-the-art research uses sample rates between 1,000 and 2,500 Hertz. Not because the brain actually generates these frequencies, but to get a better precision for the frequency phases. Finally, since we're dealing with microvolts at the first stage, it's very important to care for proper shielding in the first steps. So this is the current spectrum of EEG devices in a sensible price range. We are excluding all the medical devices here. In our community, we have the big Open EEG project with schematics and different implementations readily available, and it's already more than 10 years old. Then we have the Open BCI the OpenBCI project, which is much newer and sponsored by DARPA, so you want to choose your camp. We start with 40 euros for the cheapest and worst version of an OpenEEG. It's so cheap because it uses the ADC in your sound card in your computer. It only has 2 channels, and these channels will be quite bad. But it will work. The better alternative is this Olimex OpenEEG. It has a reference electrode, which means you won't get channel drifts or saturation problems with your amplifiers. And its ADC is much better than the one you use for your microphone in the computer. So this is the cheapest device that I'd actually recommend for beginners. The best solution depends on your budget, of course. What you pay for is the number of channels and a lower amount of noise. The best device you can get right now is the OpenBCI with 16 channels in the double configuration, but 440 euros will only get you the passive electrodes. Passive electrodes are cheaper, but they send microvolts through very long wires. So they are very noisy, and you need conductive gel to make contact with the head surface. Active electrodes have the amplifier and the ADC directly next to the sensors. That's why active electrodes are more expensive. You need separate electronics for each channel. But the noise levels are much lower, and not having to put gel in your hair all the time is nice too. The Emotive Epoch is the most compact package and transmits wirelessly and encrypted by default, but it's completely proprietary. I've heard that the transmission has been hacked, actually. Its big weakness is the sampling frequency. It only can do 125 hertz at the maximum. Then we're coming to the software. The software needs to do 4 basic things. We come on the left side. First, it needs to acquire signals from the EEG and put them into data packets. Second, it needs to estimate the location of brain activity. Third, the estimated activity needs to be processed at a signal level. I'm talking about frequency filters, Fourier transformations, and so on. Fourth, some BCI paradigms. These are the small programs that actually know what brain activity is. Let's start on the left. Fieldtrip is based on MATLAB, developed in the Netherlands, and most feature complete. It's very versatile. It's used in science a lot. But its real-time support is quite weak, so you have to hand code a lot of things. NeuroFem is a plugin for Fieldtrip. It's the only software right now that can deal with the highest quality of head models, so it's mostly used in cutting-edge science. But if you're interested, you can do this only with Fieldtrip. The most user-friendly solution is probably OpenVibe. It doesn't do localization, but it has a GUI, supports many types of EEG, and is very well documented. There's even a plethora of examples out there. And then there's Mushu. This is an alternative running on Python, mainly for people who like Python or dislike MATLAB. So when you have decided which software to use, it's time to choose a BCI paradigm. I'll give you a short overview of the most popular paradigms today. Maybe this is a good start for you guys to get into something more advanced. Steady-state evoked responses are a brute force approach to the brain. You put in a certain frequency directly through the eyes and hope that at least some neurons pick it up and convert it to electrical activity. The classic pattern is a flickering chessboard. Before I show it to you, here's a little warning. Everyone has a history of epilepsy. Please look away for 5 seconds. Really? Okay? Go. This works quite decently, right? So 12 hertz and 10 hertz. Both checkerboards were flickering at a very comfortable frequency for most neurons in the brain. They are usually at the 10 to 60 hertz range. These frequencies come in at the back of the brain, along with everything else you usually see. When you select the back of the brain with your EEG software, you will can find back this exact frequency in your spectrogram. Now the cool thing is that you can pay attention to one checkerboard and ignore the other. And in your measurement, the frequency band of the attended checkerboard becomes stronger and the other one becomes weaker when you do that. With this trick, your software can detect if your attention is on the one checkerboard or on the other. In practice, this paradigm works like mental buttons. You just press a button by looking at it. They don't even have to be big, and you can run up a dozen checkerboards at the same time. So next paradigm, P300 or oddball paradigm. In psychology, these are two different things, but in this case, they're combined. The basic idea behind the oddball paradigm is that your brain always creates the same pattern under certain conditions. The P300 signal, I show it in the next slide, is generated when we see something unfamiliar or something that doesn't quite belong into a group. The signal is the strongest at 300 milliseconds after the oddball. The strongest peak is positive, which is what the P stands for. And usually the oddball paradigm works with images or sounds, but of course you can do it with other senses as well. How do you analyze that? On the left, there's a reference P300. This is how it usually looks like when you get rid of all the noise. Detecting the P300 in a continuous signal isn't completely straightforward, because your incoming signal will be contaminated by other brain activity. So if you use a simple amplitude threshold, you will trigger all the time. A good strategy, therefore, is to use a reference signal. You take the last 500 milliseconds of your continuous signal and correlate it with the reference wave. When the correlation is above 50% or so, you know that the correct shape was actually in your signal. With this tool, you can even type on a keyboard with your mind. This is currently used for locked-in patients, for example, or quadriplegics. Just look up the P300 speller. Last paradigm, the event-related desynchronization. This is a very popular one. Event-related desynchronization is really easy to set up and very reliable. You imagine moving one of your limbs, for example, wiggling your right foot. You can actually do it, but it's not as impressive. This imagination causes certain neuronal clusters to synchronize or to desynchronize. You probably remember the waves that spread out in the beginning. In the overall spectrum, the desynchronization will create a gap in the 10 to 13 hertz range. The analysis for this is very simple. Select a region from the top right side of your brain or left side. You have to consider that the left foot is connected to the right brain half and vice versa. And take the Fourier transform and look at a few frequencies between 8 and 13 Hz for amplitude changes. Now your software triggers whenever you think of a moving foot or a waving hand. Oh, and when you look for two regions of the brain at the same time, so left and right, your software can actually detect which hand you're waving in your mind. So, in summary, buy an EEG headset, choose your BCI software, and get started. We are nearly finished. I'll just do a quick recap. Certain clusters in your brain do always the same thing at the same place, which is important for selecting a location. Memories are stored in the connection between neurons. Neurons communicate with electric waves and certain frequencies. We want to find the clusters that do what we want. Or we already know where to search from, for example, from my talk or from any other literature. But either way, we select an area on the activity map, we put the signal into our BCI paradigm, and enter the eternal feedback loop with the user. Have a lot of fun. That's it for today.
Anyone who has questions, please line up. There are 2 microphones here and the aisle there. If you leave, please leave quietly, and there's a camera already running for the guy already crossing the picture. Are there questions from the internet? Yes, no, maybe. No, then number 2.
Okay, if you want to steer some device from the EEG activity, what is the advantage of first inferring where the activity really comes from instead of just training your algorithm on the basis of the raw input signals of the EEG anyway.
Can you repeat the first part of your sentence? What is the advantage?
Yeah, so what is the advantage? What is the advantage of inferring the location of brain activity instead of directly using the raw EEG input vectors as training?
The raw EEG signal is actually not really raw because it's a mixture of several types of neural activities from different parts of the brain. So you get a mixture. And when you get this mixture, you, for example, get a lot of visual activity or motor preparation. It's all very much convoluted. And with the localization, you can actually split them up into different regions so that you only get the one signal that did what you wanted to do. So what is when your example is controlling something with this, imagining your right foot, for example, and you you take the electrode that's around here, then you will also get something from visual, also get something from audio. It's not really a clear signal, so it won't be as noise-free as when you do it with the localization before.
Okay, number one.
Yeah, when you're motivated using it for visual input, you gave some numbers about it being, I don't know, like 300 features per minute or something like that. How do you come up with that?
Arm waving.
All right.
Okay, number two.
I assume the option of putting sensors in the brain is too expensive, and that's why it wasn't discussed in this lecture, right? But I've always wondered about some kind of middle ground, as you showed in your slides, that the skull is one big barrier between the brain signals and our sensors. So why hasn't anybody proposed driving needles partially or completely through the skull to serve as the same thing? Or anything along those lines that's like relatively easy and cheap to do?
Okay, I know what you mean. It's actually being done. These approaches were one of the first steps in neuroscience at the very beginning, because you see you got it. The skull is a big barrier, and you need to go somewhere around it. So it's the easiest to actually put the sensors directly onto the brain. This is called electrical cortical activity. It's done widely in basic research. But the problem is that you need a person that's ready to open up their skull, which is usually only done when there's something wrong with their brain, and it needs to be operated or something. So all the basic research is only getting maybe half an hour per person of research time. The thing with the needles in the brain isn't so far-fetched. It's actually being done with Parkinson's patients, for example. The main problem with needles in the brain is that they are really foreign bodies in the brain. They have a median lifespan of about 6 months, and then they slowly stop working because the brain reacts to metal objects within their midst, and starts to cover all the metallic surfaces with fat. So it isn't so much of an electrical conductor anymore.
Yeah, but that's true even if you say driving the needle 9/10 of the thickness of the skull towards the brain. Does that helps none at all, or how does that work?
That would help, of course, for 90% of the variants.
As far as I know, there are some people, put things like on their head, as piercing or whatever. So.
Yeah. Actually, you could very well go completely through the brain, through the skull. It doesn't matter so much because there's still the dura mater, which separates the brain from the skull. And there, in my very weak knowledge about clinical stuff, there's no real information reaction there. But it could work, yes. It hasn't been done before because this type of EEG hasn't become so mainstream that people do it for fun. But it is very, very possible, yes.
Questions from the internet.
So, question number one. In the software comparison, the last two softwares you showed didn't have the localization options, and what can't you do if you don't have that?
Wait, last part again? Ah, here. No? Over there, okay.
What can't you do if you are missing the localization feature in your software?
Okay, you can't actually deconvolve the different types of activity that come into one electrode, which in practice means your whole signal will be a mixture of different activities, and the activity you're searching for is only maybe 1/3 of the whole activity, which means you have a higher practical noise level, which makes it harder for your algorithms to actually determine what happened in this part.
Number 2 in the back.
Well, actually, I have 2 questions. The first question is, you said the more data points you get, the better the quality is. Well, okay, basic thing. Did you ever think about trying to enhance the conductivity of hair? Like put some graphite shampoo in it or something to I don't know, maybe it's possible to use it as a sensor wire? Because your hair, I only know it in German, well, you know, where the hair is in the skin, it goes a little bit into the skin. So maybe you can use it to get a real good grid.
Okay, so the skin isn't our big barrier.
No, but you get a lot of data points. I mean, it's already in there. You just need the cabling to attach the cabling to your to your amps. I don't know. Just
Die sind nicht schleifend, and they don't conduct electricity.
No.
Hairs are
no.
pretty
So add some graphite or something.
graphite. Okay,
I don't
graphite
know.
covering for hairs. Oh, that's actually not bad.
There's a lot of chemistry going on in the is it a barber shop? I don't know. So if they make curls from it, they really do a lot to the chemistry in the hair. So maybe you can apply it in there. Just go to some cosmetic.
Okay. I don't want to be the person that connects a wire to every hair, but I think it would be possible, yes?
Okay, just a suggestion. And the second thing is, you showed that if I want to move my food, I have to think about it, and you can show that as a signal. Okay. There is also a lot of tension to my body that keeps me upright. I don't think about, and I think that is done somewhere in the back here in the motor cortex.
No. The tension thing is happening in your spine.
Okay, well, roll it back. I have narcolepsy, so I have something which shuts that off, and I don't want it. So what I try to do or want to do is to put my brain in the loop, diagnose when this tension goes away, and give some, let's say, give some electrical impulse to my muscles to regain that. Okay. Which the second part is basically proven to be possible, and now I need the sensor input and put it in the loop. So can I find that if you lose the tension of all your muscles, can I sense that with the EEG? That's the basic question.
You want to sense if you lose control of your muscles right now?
Yeah.
Okay.
Like in sleep when you have a paralysis?
The easiest, I'm not really completely familiar with basic, really basic motor stuff. Yeah. But my easiest approach would be to use an electrode actually on your muscles, so on your upper forearm, for example. Because the muscles, in contrast to the head, generate a lot of electricity, like 2 volts or so. And you can really easily measure that. And when this voltage goes down, then you have your signal.
Okay, so there is a basic activity I always have in my muscles.
It's a frequency, okay. And the frequency goes down, up and down. And of course, when you relax it, the frequency is low, and when you move it, then it becomes higher. Okay, thank you.
Okay, the internet, and then number 1 in the back.
There was a question about the organization of the hypercolumns. Are they really strictly hexagonal, or is that a simplification?
No, of course not. It was a very idealistic visualization, but this hypercolumn organization only applies for for the few flexible regions in the brain. You have a lot of fixed purpose stuff in the brain, and hypercolumns are used for a mixture of storage and computation in the general purpose areas, and there they are organized like this. But in other areas there can be, I don't know, all over the place.
Number one in the back.
So everything we talked about right now was about giving visual signals and then recording them somehow, right? But can I skip the eye and give those signals without wasting energy on the, you know, the entry sensor, basically?
There's, you want to ask if you can replace our crappy eyes with something better.
Well, yeah, that could be possible use case.
Yes, of course, yes, you can do that. The problem again is that you can't really stick some needles in your brain because they won't have a long lifetime. The back of our eyes is actually considered part of the brain. It's a completely same organization. It's the completely same cells. Technically, it's just an extension of the brain. So the retina will perform the same way like the rest of the brain does. There's actually some research going on with blind people. Okay, not really blind people. Like vision impaired people who have too low contrast in their retinas. They get implants which are put directly onto the retina. And when you put some voltage on there, then they can't see black and white images again. Funny thing, actually, we don't know how color works yet.
Number one.
Why actually did you use a mouse to go forward and backward for your presentation? Or how precise are your recognizers of what you're thinking? So why didn't you use your left and right thumb?
You mean you mean you should have used an EEG interface? Okay, actually we forgot to take it with us.
So it's precise enough, it would work?
Yeah, it would be precise enough to work. It wouldn't be 100% accurate. But since in the presentation we actually have the possibility of correcting, we would be somewhat comfortable to do this, but we didn't dare. It would work, yes.
Number two.
I've been looking for the possibilities of outside university brain-computer interfaces for some time, and basically you're the first team who speaks positively about emotive, because I was focusing on OpenBCI and I wanted to even create a hackathon, maybe in Warsaw, maybe in Berlin, somewhere in Europe, and invite the OpenBCI people, because I saw no good papers about emotive and basically dry electrodes. Can you have you experimented with them, and do you have any experiences you want to share? You could share with us.
Yes, I can. I actually bought an emotive epoch when it came out. I think it was in 2008 or so, and it was the cheapest and the most performant device at the time, and until mid of next year it still is. My major issue with it is that it's not such a great build quality, and the company behind it seemed to have regretted their decision to make it available somehow. I'm guessing it was very expensive to develop. They brought it out as a gamer accessory. They wanted people to code some games and use it as some all-purpose kind of input device. This didn't really work out because their API that's behind the whole system is not really that great. So it was used a lot for research because it's the only mobile headset right now. It doesn't produce a lot. It doesn't have a lot of channels. I mean, in research we're using more like 128 or 256 channels. In comparison, 14 is not noteworthy. And the epoch hasn't really progressed in the last 5 years anywhere. I'm not sure it has any future. But other than that, I have made quite positive experiences with it. Besides that, it only runs on Mac and Windows, which is quite crappy because I want to do it on my smartphone. And it has a relatively nice data quality. It has active electrodes, which is also nice for mobile applications. And it has a reasonably okay C++ API, which you can use to just get it out of there and get it into something, into a software package that actually can deal with brain signals.
Okay, number one.
Yeah.
Okay, this is sort of related to the first question. Do you know, are there any attempts to make the imaging more precise by using biofeedback for the actual calibration of the BCIs?
Biofeedback. Can you clarify that?
Yes, there was an art project a few years ago that I heard about called Brain Avatar, which used the direct outputs of the EEG electrodes fed into a water basin, which was then projected through an overhead projector. So you saw the wave interference patterns that were produced by the EEG, and that had some quite interesting sort of biofeedback effects too. So people could actually try to influence the patterns produced by their brain activities. And this system used, I think, 8 electrodes or something. And I wondered if it's possible to perhaps, by adding another layer, which is also directly accessible, perhaps increase the overall sort of granularity of the...
Yes, actually, displaying a real-time activity map is one of the easiest problems that you can do with such an EEG. I think it's even built in most software packages. Biofeedback is actually something of a more complicated setup because you have a feedback loop to the computer, and you, for example, use some measure of your alpha waves or something to influence something within a computer, and then it displays you back if you're doing okay or not. In today's research, this is already quite advanced. This biofeedback thing, you can learn to meditate with that. And my most amazing story was that you can actually learn how to shoot a bow without actually learning how to shoot a bow, but you lie in the scanner and you try to move one point towards another point. And when you have done that, your brain has sufficiently changed so that you can actually shoot a bow.
Number 2.
Well, I was just reading your popular questions, and just wanted to know if you have an outlook about the ultimate privacy intrusion by reading what we are thinking about or something like that. Do you have any time scale to say maybe next 5 or 10 years?
Okay, unless we solve the whole censorship in the brain issue, we are not nearly close to the reading thought stage. We actually need nano sensors ideally at each mini column, which is around, I don't know, several millions of sensors, streaming in real time towards a very advanced brain-computer learning interface that has to be trained first. What each neuron of your brain is actually meaning with its output. So it is a completely deliberate approach. You have to opt into this because otherwise the technical limitations are huge. And this is I'm speaking of a time scale of at least 20 years.
Okay, number 1.
Okay, great. So I think it would be awesome if we could read something more out of our brains, but just the movement of limbs or things that we see, and would increasing the number of sensors, say from now hundreds to thousands, help in this?
Yes.
Yes, a little.
No.
Yeah, I mean, 120 are the medical yet, and you can only buy one with
256. 256 now.
200?
Yeah.
Okay, and if you increase the number of sensors, every sensor would help you to get a better result. So thousands would be, cool, but the more the better. You can
so why are all the systems that we see just with these sensors every few centimeters and not every millimeter?
It's the main reason is actually price. It's just so simple. An active electrode, one channel, costs around 520 euros for medical results.
Economy of scale?
Yes, and I'm expecting that it becomes cheaper with time, but the problem is that we have to get magnitudes of more sensors, and the price is only going down slowly.
Okay, number 2.
Yeah, given the plasticity of the brain and the tendency to kind of move functions around that you see when parts of the brain is damaged, these columns, are they easily identifiable? And are they identifiable by the signals or?
No, not at all.
No.
The resolution of today's EEGs are nowhere near in identifying single columns. We still need 15 years for that, and the according sensor increases.
Okay, number 1 in the back.
Just to continue the question before, you said you can make people that are blind see black and white images, kind of.
Vision impaired.
Vision impaired, sorry. But can I show them pictures that are not those that they see?
Yes, definitely.
So I already know how it's encoded.
We know how the retina is encoded, we know how the back of the brain is encoded, which would be a much
And
better,
we know how to
place.
create the signals that we need.
Yeah, that's also no problem. We don't know how color works. That's the only
Yeah, but
limitation right now.
that's side effect.
If you want to actually, if you actually want to input signals into the brain, then you shouldn't use your retina. You should use the back of your brain because there's much higher resolution there.
Thank you.
Okay, number 2.
So I had a conversation with a neuroscientist about a year ago about much the same issues. There are 2 other technical difficulties he recounted. One is that the data rate from a decent EEG is really high. 2 is that in trials with rats, where they implanted electrodes, the areas on the brain tended to move around, so the needles that you stuck in one day didn't exactly correspond, didn't exactly communicate with the same area anymore after a while.
Okay.
Because the area itself moved.
Mm-hmm.
I don't know how relevant this is, or if it's just a web thing.
Areas themselves, in humans at least, don't really move that much. But single neurons can move up to a centimeter per hour.
Huh.
So it's, I would say that it is an issue, but with our current technology, what we do is we stick at most 64 electrodes in the brain, and this at a grid of 1 millimeter. It shouldn't be that much of an issue. If it's an issue, then you have to recalibrate after every week or so, I don't know.
Okay.
Okay, thank you, Dominic and Anna.